So in this section, we're going to start our work with exponential functions. So we're going to go through an example to kind of get an introduction, and we'll get this comparison of linear functions, which is something we've used a lot in algebra so far, and comparing that to our new function, exponential. So we're going to look at this real case from 1988 with a judge in Yonkers, New York. And this judge ended up giving two fines. Fines to some councilmen and fines to the city of Yonkers. So in this, it's just to give you some background on why the judge instituted the fines. So you can read up on this information behind here from a New York Times article. But in terms of getting into the math of it, we're going to focus on what happened here on August 2nd. So Judge Sand fines the city and the 4 councilmen who voted against the amendment in contempt of the court and imposes fines. The city's fines start at $100 and they double every day. So they start at 100 and then they're going to go 200 and then 400. So doubling every single day. And then for the councilmen's fines, they start at $500 a day and increase by $500 each day. So where we're going to start is making a table for the councilmen and a table for the city of Yonkers to see how these fines escalate as days pass on without them being paid. So with the councilmen, so this is where it starts at $500. It starts at $500 and increases by $500 each day. So on day 0, they are being charged $500. And then a day passes and they get another $500 added on. And then another $500 added on, and it's just increasing by $500 each day. So let's think in terms of a formula. So on day 0, it's just that initial starting value of $500. Day 1 came from taking that initial $500 and then adding on this additional fine of $500. On day 2, and this is where I'm going to organize this in a way that helps us with our formula, the idea being we have this initial value of $500, and then we're adding on 2 days worth of additional fines. So we have this 500 additional fine 2 times now. And then on day 3, we have the initial value 500, and then we're adding on this extra 500 3 times, and so on and so forth as we go down here. So what this would look like in terms of a formula in general for any amount of days that has passed, what we would have is that initial value of $500 plus this additional $500 per day. So this is where we can see this is a linear equation, coming from the fact that we have this starting value and then we're constantly adding on the same number per day, which is the idea of slope of a line. So it's constant and being added on for each day, where we could plug in t for the amount of time. All right, let's look at the city of Yonkers. So their fine starts at $100. So on day 0, they're being charged $100. And then their fine is doubling every single day. So if we're starting at 100, then we would have 200. And then that would double, and double, and double, and double. So in terms of a formula, so we're starting with this initial value of $100. On day 1, if 1 day has passed, then we have that $100, but we double it. If we're on day 2, if we take that $100, for day 1 we doubled that, and then for this day 2, we then double that. So it's like we can see day 0, day 1, and we want to double the results from day 1, so that's where we take that times 2. And then if we're at day 3, we have 100 doubled from day 1, doubled for day 2, and then we would double it again for day 3. So you have this 100 times 2 times 2 times 2. And as you can see, we're going to start having this long string of multiplication by 2. So what we can do is simplify it in terms of an exponent. So that's the same thing as 100 times 2 cubed. And then for day 4, I would have 100 times 2 to the 4th power, and 100 times 2 to the 5th power. So this idea that we're multiplying the results as our function changes, that's going to give us an exponential function. So for, in general, with a variable t, we would have that starting value of 100 times this idea of doubling, and then our exponent goes, our variable goes into the exponent, and that's what makes this exponential. So if we just kind of compare these two graphs or charts, and we can see, so the councilmen are starting with a larger fine, and it seems to grow by a lot, like $500 being added on every single day. But what you can see with the city of Yonkers is it starts at a much lower value, that $100, but by the time they reach day 5, they're pretty close in owing the same amount. And if you can imagine, if we went to day 6, if we went to day 6 for the councilmen, they'd be at $3,500. City of Yonkers would be at $6,400. So we can do is compare how they change. This exponential function is going to change a lot faster. It's going to increase to larger amounts a lot more quickly than the linear function. So let's look at the graphs. So if we graph the two functions, so the councilman starts at 500 and then increases by 500 each day. So as we said, that's our linear function, and then that would continue on forever. So some things I want us to note here is this is linear, and it's increasing by a constant amount. So it's a constant amount that's being, in this case, added on. For linear, it could also be subtracted on. That's the idea that we're adding on this amount. And it being a constant amount that we're adding on, that's our idea of slope for a linear function. Now, our equation that we got, that y equals 500 plus 500t, the pieces that we get from this, that first 500 that we're talking about there is that initial value, the idea that their fine started at 500, and then they said, then you're going to add on 500 per day, and that was our slope, or this constant amount of change, or this constant amount that we're adding on per day. So let's compare this to the city of Yonkers. So this one started at 100, and then we went 200, 400, 800, 1600, 3200. So as you can see, this isn't a constant slope that we're seeing. The slope changes. So with that, we want to connect this with a smooth curve. So we're going to connect the dots, and then we'll go off to positive infinity. So this is exponential. And what we're increasing by here is a constant factor. This is coming through from multiplication, as we saw written out in the table. So this increases by a constant factor, which factor comes through with multiplication. So when we have this y equals 100 times 2 to the power of t. That 100 is our initial value, so it's where our graph is starting. And then that value of 2 that's under the exponent of our variable, the base of the variable, that's going to be called our growth factor. So we're seeing 2 there because of this idea of doubling or multiplying by 2. All right, so there's some key characteristics to our exponential function, comparing that to our linear function. So let's look at some questions that we could answer. So on what day will the city of Yonkers fine reach over $1 million? So what we're doing is with our function, we want to see where the fine is $1 million. And when is that going to equal 100 times 2 to the t? So, solving for our variable, we could divide both sides by 100, which would leave us with, well, we cancel out 2 of those zeros, so we'd have 10,000 equals 2 to the t. Now, at this point in our course, we don't know how to solve for that variable there. If you've learned logarithms before, which is going to be our next section, well, spoiler alert, that's going to help us solve this. But we haven't learned them yet, so what we're going to do is look at the graph. So we're going to go to Desmos and solve this graphically, meaning we're going to make a graph for the horizontal line of 10,000, and we're going to see where does that intersect the graph of 2 to the t. So if I go to our graph, you can see here in Desmos, I graphed the line y equals 10,000, so that's showing up in red right here. And then I have y equals 2 to the x, and what I want to look at is that intersection point. And what I see is t equals 13.288. So what that tells me is that between the 13th and 14th day, the fine will reach $1 million. Or you could say like the fine will reach over $1 million on the 14th day. Like 13's a little too early. At 13 would still be below 1 million, but if you're at the 14th day, then you'll definitely be over 1 million. So, how much will the city of Yonkers be fined on day 30? So with this, we're just plugging in t equals 30. So we're going to take y equals 100 times 2 to the 30th power. Now this is where, like, plugging in 30 into a linear equation, which actually we'll do for the councilman, so this is for the city, and then for the councilman, plugging into the linear, so y equals 500 plus 500 times 30. What I want us to notice here is the difference between plugging in 30 into a linear function versus an exponential. Plugging into linear, the instinct I want you to have is the number will be big, but it won't be as big as what's happening with an exponential. Like this growing exponentially, as we can see from the end of our graphs, like we talked about, this is going to keep growing so fast, where this is just going at a constant rate. Not slowly, but slower than exponential. So while we're just seeing a glimpse to day 5 here, or even day 6 almost, going to day 30, these are going to be very different values. So we're going to need a calculator to help us out here. So I'm going to go back over to Desmos and get to the scientific calculator. So we want 100 times 2 to the 30th power. Now, the calculator here is giving us scientific notation. So what you're going to do here is it basically tells you how to move the decimal place. So with this, what we're going to do is, since it's positive, we move the decimal to the right. If it was negative, we move the decimal to the left. So with this, I would move the decimal to the right 11 times. So go 1, 2, 3, 4, 5, 6, 7, 8, and then you can notice that I can't see any more beyond that. So with that, we could just start filling in the blank with zeros. We could go searching for a more powerful calculator, but I'm just going to go ahead and stop at the 2 and then fill in the blank with zeros. So let me count that again. That was 1, 2, 3, 4, 5, 6, 7, 8. So then I need 3 zeros, so I go 9, 10, 11. So I'm going to take that number and put 3 zeros following that 2 there. So that's where we get a very big number out, so much so that the calculator doesn't even want to write it out. 8, 2, and then 3 zeros following. And if your calculator just lists out the number for you, that's awesome, but I wanted to make sure we see that scientific notation, especially when dealing with exponential functions, and we can get these really big values. Similarly, we can also get these really small values, so we need to know how to move that decimal place around. All right, for councilmen, that's going to be a much smaller number with 500 plus 500 times 30, which is 15,500. No extra work to do there. 15,500. So on day 30, this is the difference in amounts between the city and councilmen, and the difference between having something exponential rather than linear. All right, so our exponential function, the breakdown of it is we'll have a function where you have a times b to the x. What makes it exponential is that our variable is in the exponent. The exponent. So that's the key piece. A is the initial value, so it's the starting value, or you could think of that as where we plug in x equals 0. So if you look at f of 0, what you would get is a times b to the 0 power. And just remember that anything raised to a power of 0 is equal to 1. So really that's an a times 1, which is just a. So it's kind of like it's the y-intercept of this function. And then our other piece is the growth factor, b. It has to be more than 0, and it can't equal 1. Because if you put 1 right there, as you can imagine, if you have 1 with any exponent, it's just 1, and then it doesn't really do anything. So we'll talk more about the growth factor in future videos and kind of interpreting it. But there's our introduction to our exponential functions.